Hi, in this video, we are going to show how to convert our rates for different units of time. Now, in this first example, we have in 2015, a beekeeper experienced a dramatic loss of their 56,000 honeybees, with 42.1% of the colony bees being lost within a 12-month period. They want to know the yearly decay rate. Well, just remember, for a rate, you move the decimal 2 places, or you divide by 100, and you get our rate is 0.421. The next question says, assuming the trend continues, write an equation to represent the population of bees left each year. So because it's decay, we're going to start with A equals P times 1 minus R to the T power. Our initial value is 56,000 honeybees. And we have 1 minus 0.421 to the T power. We can even simplify that and write 56,000. This ends up being 0.579 to the T power. And it's important to represent that T is in years. Now, you don't have to write that. You just need to recognize that because it is a yearly decay rate, and we're writing an equation based on years. Now, they want us to write a equation to represent the population of bees left each month. So for example, if you want to have the population 6 months later, you could put in 0.5 for T because 6 months is half of a year, right? But we could also write an equation with M for months instead of T for years. Now the way that we're going to do that, and the steps are on the side, our base right now is yearly. And that yearly base is 0.579, and we have an exponent of T, where T is years. Our goal is to write it with a monthly base. Now, they are going to be equivalent because, well, the rates won't be equivalent, but I mean, the expressions are going to be equivalent because we're really not changing anything about the problem. So we're going to start with what we have, and we have 0.579 to the T. Now, think about it. We have a whole year. We don't want a whole year. We want 1 month. In fact, we want 1 out of the 12 months in a year. So we want 1 out of the 12 months in a year to go monthly, 1 month at a time. But now they're not equal because I just made an exponent of 1 over 12. So I need to balance that with a 12. I didn't change anything because 1/12 and 12 cancel each other out. So these are still equal. But now what happens is if I put this in the calculator, 0.579 to the 1 over 12, I get something new. And it says to round to the nearest tenth. So all of this becomes, oh no, it went away. Okay, we're not rounding to the nearest tenth. We're going to round to the nearest hundredth. That way things make sense for us. If we round to the nearest hundredth, it's going to be 0.96. And now I have a new base, and I'm going to copy down the outside exponent, what I didn't put in the calculator. Now, this is still T for years, but we could take the exponent and we could write it as 0.96 M, and this will be months, where this is T for years. And you get a new equation. Now we have A equals 56,000 bees times 0.96 to the M power for months. And if I have 6 months, instead of writing, oh, that's half a year, I could just plug in 6. But now the question is, what's the monthly decay rate of the bee population? We were losing 42.1% of bees per year, how much are we losing per month? So let's take a look at it. We have 0.96 is our base. This is a decay function. And hopefully you see that your decay rate is 0.04, meaning we're losing 4% of the bees per month. And when you're talking about it overall for a year, that ends up being, how much was it per year? 42%. Okay, we're going to try one more problem. The Speedy Foot Shop has been selling a newly designed skateboard. The board has been very popular, and the shop has seen a 4.25% increase in profits over the past year. If this trend continues, which expression could the shop use to approximate the monthly percent increase in profits? So we're increasing, so this is going to be a 1 plus r to the t type of problem. Notice they didn't give you an initial. We can't write the full equation, but we have the growth factor. And remember, the growth factor is the base. So we have 1 plus, not 4.25, but 0.0425 when you convert it to a rate. So we end up with the yearly rate, our base being 1.0425 to the t power, where t is years. We want to go to a monthly rate. Now, these are still going to be equivalent because it's the same scenario. We have 1.0425 to the t. We don't want the entire year. We want 1 out of the 12 months in the year. So 1 out of the 12 months in the year is what we want. We want to go smaller. But this is no longer equal. So if you take a 1 over 12 exponent, you need a 12 to balance it out. You're going to take what is inside the parentheses. All of that goes in the calculator. And we get a really long number. But notice how your answer choices stop after 5 places after the decimal point. I'm going to stop there too. So this becomes 1.00347. Now your exponent, what was there, really stays the same. So all of this is just going to be dragged down as 12t. And sometimes this is an answer choice. But really what we're looking for is now to replace the exponent because we converted to months. And we're going to replace that exponent. We no longer need a t. We're going to put m for months. And that ends up being choice 3. And you can see that it increases, like the rate here. A rate of increase is about 0.347%. Anyway, I hope this video helped. Just as a heads up, as a multiple choice strategy, if you're increasing, if you have a factor of 1.0425 per year, if you're converting to a different measurement of time, it should change. So if you start with 1.0425, go and cross out the answers that have no change at all. And then it's just a guess between choice 3 or 4. Now try the next two on your own.